Okay, good morning everyone, and welcome to the third and last day of the conference. I will be chairing the first keynote session, but as we did with the previous one, before I introduce our speaker, I would like to share with you a message from one of our sponsors. This is Quanser. So thanks to Quanser for their contribution to L4DC. Let me switch back to the presentation of our keynote. So I have the great pleasure to introduce today Jonas Buchli. Jonas is a senior research scientist at Google DeepMind based in London. And before that, he was mainly based in Switzerland, leading the robotics group there in the mechanical engineering department. And before that, he had obtained his PhD degree from EPF in Lausanne, so from the other side of Switzerland. His research is at the interface of control and machine learning, and he has covered a series of applications ranging from robotics, which is the main focus area, but also interdisciplinary projects going from biomedical technology to paleoanthropology. It is our great pleasure to have Jonas here today. His talk will be on the intriguing topic of going through the state of art of optimal and learning-based control in the 2020s. So we look forward to that and the discussion afterwards. Please join me in welcoming Jonas on stage.
Okay.
All right, this is on. Can you hear me? All right, great. Good. Apologies ahead of time for breaking the rules. My voice is a little, you know how this is when you go to hotel rooms and they freeze it down to near absolute zero. So hopefully this is going to work out. All right, I would like to talk to you a little bit about optimal learning control. Let's see if this works. And to sort of warm us up, I want to reflect on what the practice of control theory and engineering actually is. And this is sort of my definition that I put up. I'm sure you have your own. So it's the science and engineering practice of getting certain quantities of systems to behave in a desired way. Now, I'm sort of focusing a little bit on that word practice because I think it's useful sometimes if we zoom out a little bit and actually reflect what we're actually doing than only just looking at the, the mathematical and technical details of things, and I will come back to that. So in that spectrum, obviously, we have a lot of things that fall into that bucket or into that definition, all the way from simple and well-understood problems like temperature control in a room, over sort of like more complex examples like aircraft control, which obviously spans a whole range of complexities, all the way to really difficult problems like, for example, controlling the interest rate in a country which is a problem that is at best sort of partially understood, right? But all of that sort of fits into that definition. Now, how do we go about sort of solving, what is the practice that we're doing? And I would sort of, on a high level, I would say there's three major steps. First, we need to sort of understand and model our problem, and then we solve that problem that we just, modeled, and then we deploy it. And these are then sort of iterative processes, and in itself, every steps and overall, and many, many iterations. And this is sort of well reflected. Does it have a laser pointer? Oh, yeah. This is well reflected with this little sequence of pictures. So basically, this is sort of the first controlled turn in aviation history, more than 100 years ago. This is sort of like a picture around World War II, when the first autopilots came up all the way to like modern sort of control and guidance systems. And obviously, this is just to drive the point home that also, when we say iterate, there's many, many people that are possibly involved in solving problems over many years. And these iterations happen not just for one person, like within, let's say, a PhD thesis or a project. But in a nutshell, really sort of what it means, so we need to understand, model the real-world control problem. We translate it into what I call a mathematical control problem. We then solve that mathematical control problem, and we implement the solution, confirm its correctness, the performance, and deploy, and we iterate over that. Now, I would say, particularly in academia, but also in parts of industry research, there has been a lot of focus on this number too. And so the traditional view on that is obviously something like this. I mean, there's many different variants depending, what sort of school of thought you are. But in a nutshell, it's basically this sort of focus on this gray box where basically you have a planner, you have a plant, and you want to basically make sure that your plant behaves like the planner wants, and sort of if you need to figure out how to fill in this gray box, that's sort of like the control problem. Now, if you, until about 10 years back, I would say, if you were dropped sort of like such a fairly complex system with maybe 30, 40 degrees of freedom, and there's many actuators, you would have a challenge solving that. There were maybe candidate solutions that looked promising, but it was not clear yet how to solve that in 2010, 2012, and so on. Now, fast forward, in the 2020s, it seems like we have cracked that problem, right? I mean, this is just an example. There's obviously other ones, and I could as well also use a picture of like a real robot here. We can solve such complex control problems in a very, very nice way, and they will come back to this example. And this is just, this right picture here is just to say, this is not only true for machine learning, right? I mean, there has been a lot of advances in other parts of control engineering as well, where basically you can do really impressive things, and which help us basically doing things faster and more robustly and better. But I'm going to focus here on the left side, so I'm looking at the reinforcement learning side of things, and I want to sort of look back a little bit and see how did we get there? How are we solving? What enabled that fast progress in these 10 years? It all starts with the optimal control problem, right? And this is literally what we're doing in reinforcement learning. We're solving the optimal control problem. This is a very generic way of how I wrote it down here. There's many different ways you can write it down. And so typically, right, in the optimal control problem, we have somewhere a sort of a system dynamics, something that generates like state trajectories, let's say, over time. And in this system dynamics, we have a part we can influence. That's your control or a controller, right? You can stick something in there to make, hopefully, the world behave a little bit your way. But we usually also assume that there's some parameters or something that is fixed but maybe unknown, or maybe we can partially model it, which is sort of the world or the system dynamics. And then we pose a reward or a cost if you're basically maybe a bit more from the optimal control point of view. That's just sign flip. The math works out exactly the same way. And then the problem is obviously finding that optimal control policy, so basically that I can stick in here to maximize my reward or minimize my cost. Now, this is, as I said, this is what we're solving head-on with reinforcement learning. Obviously, there's also other flavors of control, right? More classical optimal control that solves the same thing. The difference is not that it's not where we're starting from, but it's basically the assumptions that we're making along the way that we are willing to make, that we want to make, that we have to make, that they're imposed on us for some different ways, but we're making assumptions. This then separates sort of the different strands of how we solve this problem, right? Let's say if we solve LQR, we have to take a smoothness assumption, linear time invariant system, for example, or if we do iterative, we can do still nonlinear systems, but they have to be smooth and so on. And sort of typical assumptions in reinforcement learning they're a bit less maybe stringent than some of the assumptions are done in other branches, and this is maybe that's actually some of the distinguishing factors. So the typical assumptions are, we assume that the system is Markov. So in a nutshell, what that means is that your system has sort of a finite memory that you can sort of observe. Usually things are actually formulated in discrete time. Yes, there's continuous time approaches, but they very quickly switch into discrete time. We usually, at least at the outset, assume stochasticity, but that's actually, well, we can talk about that. We assume an observability, and this is an observability that is different than in control engineering. So this is basically, in a nutshell, what it means is we can observe the state well enough that we can compute our rewards and that we can distinguish them, right? Basically, that we can sort of make a reasonable Q function that is can distinguish where we are and give the proper reward. Yeah, don't want to go too much into technical details. And then usually, more often than not, we assume a discounted total reward. So basically, just a sort of a discounted sum of intermediate rewards, which basically build our reward that we want to maximize. Good. So this maybe comes a little bit as a surprise to some, and maybe even people doing reinforcement learning, is that I would say actually to do this, usually a lot of model knowledge is required, even if it's maybe not assumed or people are not very conscious about it, but there's a lot of model knowledge that goes into that. And they're going to come back to that point. But okay, how do we go about solving that? And this is just we're going to fly on a very high level, okay? And your pilot is somewhat opinionated on these things, one eye blind, so forgive me if I blaze over a bunch of technical details here, but there's this concept of a value function. And again, this is familiar also to people that do classical optimal control, right? It's the same thing that you see there. What is it in a nutshell? Basically, well, it's the expected total reward that you get when you start in a given state in a system. And basically, the traveling salesman example that you probably know, it's the length of the path when you start somewhere and then you travel a given fixed travel plan afterwards. And there's a special value function, which is the optimal value function. This is just the highest value, the highest, sort of the best scoring value function that you can get. So it's the expected total reward when you start in a given state and then follow this optimal policy, the optimal control policy. In the traveling salesman problems, what that is, it's the shortest possible length of a path, right? When you basically, you're in a city and then you follow the optimal travel plan. We haven't yet discussed where that comes from, but the take-home message is actually the important thing. If you have this value function, you have actually solved a large part of the optimal control problem. Because what you can do then, you just locally sort of have to hill climb or hill descent in the steepest way, right? This is what your optimal controller needs to do. And this is sort of a very, very important quantity that shows up everywhere. The catch with this function is that they are mathematical beasts, right? Because they live in a very high-dimensional state space, or state action space. So if you think about the humanoid example, the value function would be over like this 40 states, plus, well, actually it's twice as much because you need velocities as well. So 80 states, and then as many actuations, right, and so on. So they're really, really large, function of a very large space. Solving for them is generally very hard. Yes, we do have differential equations for them, or difference equations like the Bellman equation or the Hamilton-Jacobi-Bellman equation, depending if you live in the continuous or discrete world, but they cannot generally be solved analytically. Now again, I'm coming back on this assumption, right? Of course, now we can make some assumptions, and then we can do certain, for example, numerical solutions like what LQR does, right? If you remember the Riccati backwards pass, what you solve therefore is actually the value function, but you do it locally, right? In particular, if you do like iterative optimal, like sequential linear quadratic control methods like SLQ or ILQR, things like this, you basically sort of start somewhere and you solve your value function locally around this trajectory where you're solving from. The question is, can we do this in a more global way? And this is basically what reinforcement learning gives us, or the deep reinforcement, or the latest crop of reinforcement learning. And there's the three keys in order to do this. The first one is the insight that basically, well, I can sample or I can estimate the value function, so this really important quantity from samples of the real system, right? Basically by remembering that there's this relationship between, and yeah, this is now not a discount. I dropped a bunch of things here, so this is just a non-discounted cost here. So this is the expected total reward, right? This is basically my value, an estimate for my value function at a given state S. I can possibly bootstrap this, is sort of important, so I don't have to necessarily, if there's a very long trajectory, I don't have to go all the way, I can bootstrap with my estimate. The second key is realizing that, and this is a very important point, because this is literally where it switched from, okay, these are toy examples to real, right? In a simple system, you can literally enumerate that. You can make a little table, right, and say, okay, these are my value function, and I think most of you, or many of you have done that for some toy examples. And this is sort of where we were right in the 90s and 2000s and things like that. And that's also a little bit what brought some, I think, disdain and scorn from some people to reinforcement learning, because they say, well, what are you doing with your grid worlds? This is never going to scale. And then basically some smart people said, well, actually, I mean, we can do function fitting, right? So let's fit some functions. Let's not make tables. So maybe we can do this better. But obviously, this is still hard, because these are over large state space. So we'll come back to that. But you need a loss function for that. The loss function is, in essence, the third important key, is the principle of optimality, literally the Bellman update that you basically apply to that to formulate sort of a TDR. There's many different variants. Again, I mean, I'm brushing over a lot of technical details and variants here. But in a nutshell, so you can formulate fairly straightforward losses that you can then use to fit. Now, as I said, this is still hard, because you want to fit a function over a really large state space, and this is known to be hard. But this is basically where deep learning comes into the picture. And deep learning, I would say, is sort of a synergy, and it's not, I don't think it's for random reason that this has happened in the last 10, 20 years, right? Because it's a synergy of a few technological advances that came together that really changed the game here and made basically this idea of function fitting possible. The first one is basically the realization, this is older obviously, this is quite old, that there are very efficient function approximators. So when I say efficient, basically if you compare sort of the expressivity to the parameter count, which are sort of deep, uniform computational graphs, right? And this is obviously your neural networks. I really don't like the term neural networks for many reasons. So this uniform basically graph is very efficient to fit functions. Then together, there's another advance in computer science, which is automatic differentiation. I think this is completely underappreciated, basically which lets you automatically and precisely get you any derivative of any computational graph you have. Not approximate derivatives, but exact derivatives, and it's fast, right? Taking these together give you efficient auto-differentiable function approximators. So now you can get, basically from even large graphs, you can get any sort of gradient that you want. Then, of course, you can use this now to formulate cost function losses to optimize. And there was a lot of progress in large-scale optimizers, so algorithmic progress, sort of subsumed here on the stochastic gradient descent, how to stabilize that. So it's really a hard problem because you get really, really large gradients. How do you do this? But also software infrastructure matured, right? So you got a lot of like really mature sort of software packet infrastructures that let you do this without having to know all the details. And then something that we should not forget, I mean, compute and storage. So like how many dollars you pay per flop and per byte of storage just came down. And finally people sort of could, with reasonable cost, start doing and putting this in practice. And that is obviously not just true for reinforcement learning, actually. I mean, in supervised learning, this came first, right? But now we're applying this idea to fit the value function of polygon. This is in essence what completely changed the game for that problem that we're trying to solve. All right, this is a quick summary. If you were still tired and were sleeping through the first part of the talk, quick deep RL in 3 bullet points. We're aiming at solving the optimal control problem. We need to fit the value function, which are functions in a very high-dimensional space. And we can use function approximation and iterative fitting to do this. Now, I haven't talked about data yet. We need data to do this. And actually, we need lots of data. Where does it come from? And how do we generate this? So that was another insight basically that emerged. So basically in the last 10, 15 years is that you can separate basically the collecting of the experience and finding the value function at the optimal policy. These are two quite separate, no, I would say actually completely separate problems. Let's put it that way, in this extreme form. And you know, when you go back to like certain part, you obviously have like this policy improvement steps, that improvement, evaluation, and they're all sort of intertwined together, right? But actually, you can just sort of like take a big scissors and cut this apart and do one step first, the other step after, or mix it. And this basically lets us doing things in quite different ways and gave us many different ways of doing reinforcement learning. Now, we have lots of options to collect the data. There's the online one, that's sort of the more traditional way, the one where basically you really use the policy or a slight stochastic variant of it that you're learning to also explore. You can do offline learning, so you just use a fixed, can be a completely different policy to generate data that you're learning from. You can use existing controls and policies. They don't have to be machine learned one. They can be your linear best controller or something like that. Can also be from expert demonstrations like humans or expert controllers. So human design controllers, they can come from models, right? It's what we do a lot, usually via simulation. They can come from the real world, so you can roll out on a real system. And we can completely mix this up, right? We can take a little bit of that, a little bit of this, and mix it. And this gives us a lot of freedom, basically, to do whatever we need, what is the best for the given task. But one thing to note, and we're going to come back to that, the only way how you can infuse domain knowledge to your learning agent is via sampling, right? The agent has to basically go and sample from the world or from the model, and there's no other way. You can tell your agent, well, no, there's other ways, but let's leave it at that. There's almost no other way to do that. Now, it's not all golden, right? When we collect data, this is it's actually, I would say this is the less solved part of the problem. I mean, we can optimize very well large problems, turn the crank. But you know, collecting data is hard. That's for a good reason, because there's this exploration problem, which is actually sort of like a unsolved, probably unsolvable problem. Some might say it is ill-posed, some might say it is AGI complete, whatever. I mean, it's just, where do I go and collect data? Who tells me where good places? If I only know what happens here in the world, how do I know that I have to go out there and find my good policy, right? It's a very fundamentally hard problem. The data might not have the right property, there might be bias, might be not diverse enough, might be not sampled the right assumptions, not enough data, right? That's sort of critical. And we come back to an example where this is actually true. Collecting in the real world, obviously safety concerns, and a lot of people in this community think about this. Wear and tear, right? Your stuff breaks if you're not careful and you just randomly explore. How do you do resets? How do you establish rewards? It's actually often a hard engineering problem in itself. And then, you know, when you collect data from simulations, say, well, I don't want to do this in the real world, then obviously simulation, your model is always wrong. Well, this is the same tutorial gap. Is it critically wrong? Well, we don't know. But actually, what often also happens is that the simulations have actually outright bugs and exploits, which basically is your learning agent, you know, solves your problem excellently in simulation, but this just doesn't transfer. So one fun example was when we tried to sort of learn how to pick up boxes at some point, and the agent would just figure out it can just go real fast and punch the arm through the box and lift it up. Now, it is obviously not the solution you want in the real world. It's because of the way the contact model works in simulation. But you know, the simulation, it's a solution. So the agent obviously locks into that and totally exploits it. Now, how do we specify the solution, right? So we have to design a reward. And I just want to juxtapose this, because that's actually also, I think, where sort of like we get some niceties of reinforcement learning in contrast to maybe other methods. Because classically, we do a lot of divide and conquer, right? So if you have this problem of an arm that, you know, has to put that banana into a box, I have to start thinking real hard and start, you know, maybe I put some coordinate systems at the fingers because that's what I want to use. Then I have to, you know, refresh my differential kinematics and dynamics and put a coordinate system in the banana and formulate differences and then map it into the joint space and then implement the joint controller and so on, and until I finally can find a tracking controller that I can sort of, you know, implement and solve this problem. Now, in reinforcement learning, this is a little bit easier, at least in principle. So, because in principle we can specify, we don't have much constraints on the reward function. We can sort of have a very unspecific cost function. Let's say 1 if the banana is a basket, 0 otherwise. And then basically, so what we do, we sort of specify what we want and not the how, and then the algorithm figures out how to implement the solution. So a bit less constraints, and in particular, I'm going to come back to that. We don't need to specify a separate planner and controller. In principle, the algorithm solves both problems at the same time. Right, it will infer how to fulfill this task and how to generate the plan and how to track the plan. Okay, so not as much separation of concerns needed, but also, of course, I mean, that's sometimes it's nice if we have sort of intersection points, right, where we have a point where we can inspect the system. So it's just to say there are two sides of the medal here. But yeah, I just want to illustrate real quick what sort of the nice solutions that you get, right? Here's a robot arm that needs to clean up. It needs to put these little objects into the box here, it has a lid, it has to open the lid and then put the thing in. If we come with our engineering goggles on, right, then we would say, okay, I put coordinate systems here, I put coordinate systems at the end effector, I make it sort of that the distance gets smaller to the grasp points, and I forgot I need to open the box, so let me use the fingers to open the box first, and have a little state machine, and then if that's successful, I go and take the block and put it in there. Now, if you let the reinforcement learning algorithm loose on that, it does a little bit different, right? It uses parts of the robots that you wouldn't think about as coordinate systems, as targets for your control, so like the fingers or even the blocks or the wrist of the hand, and happily just use this to open the box very quickly, and then in one swoop basically put these objects in. So this just illustrates a little bit how if you give the algorithm sort of this freedom that it can be fairly creative, but that also obviously, right, safety and stuff, creativity is not always only good. This video that we already have seen sort of helps us illustrating that, right, we can solve the control and plan simultaneously. So it's basically, in a problem like this, if you don't have a plan and a control that works very tightly, very well together, it's not going to work, right? It's not going to happen because you have sort of varying obstacles here that you have to solve from the visual policy and so on. And so this is just an illustration for that. There's many others that you could put up here. Okay, but maybe in the reminder, I want to talk, before closing the talk, I want to talk about sort of an application. I mean, it's a tentative application where this might be useful in the future. And this is basically controlling nuclear fusion reactors. So running AI on a tokamak. This is work that we did together with EPFL. And basically, since I appreciate that not all of you know how fusion control works in detail, I just want to round through that before we see a bunch of results. So nuclear fusion, the idea is that basically you take two atoms or two species of atoms, put them together under pressure and under heat, and that they start fusing, and then the product, so typically it's done with deuterium and tritium, the product is lighter, and the difference in weight you get as energy. And this is not a lot of joules per species, but obviously you do this a lot, and then sort of you get a lot of energy out of that, and that this is possible. There's a proof. It's up in the sky. It's the sun, right? It's happening there. So we know this is physically possible. But if you want to do this on Earth, you actually have to keep this hot plasma, which, by the way, for technical reasons in tokamaks has to be at least 10 times higher than the surface of the sun. So it's going to be the hottest thing in the universe on Earth. You have to keep this away from other parts of your system because otherwise it's just going to melt down. The way, or one way to do that is putting it into a magnetic bottle. This is what is called the tokamak in the form of a torus that is sort of wrapped with magnetic coils, and you use this magnetic coil to manipulate the magnetic field such that the plasma stays in place and does what you want. Okay? I'm going to show you some examples on the TCV. This is le tokamak. It's not the tokamak. A configuration variable, we're going to come back to that, which is a research tokamak in Switzerland. It's over-instrumented. It has a lot of control cores, so we can do a lot of cool things. Now, going forward, I will show you mostly these 2D sections because it's a sort of rotational symmetric thing. So we only look at these 2D sections and can discuss the control problems in that. Here's a little view, fisheye view. So basically, this is what we're seeing here, the chamber. Right, so basically, a configuration variable means variable configuration tokamak. So what I mean by configuration is plasma shapes. And so TCV can do many different shapes, sort of, simple ones like round, more elongated, triangular ones, but also more funky ones like these little balloon-shaped ones, right? And you can see that the more you go over here, your field lines become more complex. So, many different variable configurations. And that's why this is interesting. So it lets physicists study many different plasma configurations, what their properties are, and how it could possibly be used. That's what they want to do. The way we control that is basically, as I said, so we sort of look at the magnetic field and try to manipulate that with the control coils. We have 19 actions. We have up to 120 measurements. These are sort of magnetic flux loops, which are distributed over the surface of the tokamak. We need to do this at 10 kilohertz in hard real time, so not a lot of time to think for your neural networks, if that's what you use. It's highly underobserved, just reminding us of that. So the goal now is to find a controller that takes this up to 120 measurements, plus targets, what you want to do, time varying. We use up to 40 targets that we're tracking, and then basically produce voltages for the coils that control the plasma. Now, the real tokamak as an environment is unfortunately not suitable for learning on the real system. We can only do like about 2 seconds of runtime at 10 kilohertz every 15 minutes. And basically, so there's limited experimental time. And also there's many teams, right? It's oversubscribed. There's a whole European or worldwide research community that wants to do work on that. And then also the historical data is actually too small. And it's collected under too diverse conditions. So, well, what do you do? The reinforcement learning answer is that, well, give me a simulation and I will solve your problem. If you have one, and luckily here, for this problem, at least for the first problems we're trying to solve here, we have such a simulation which runs fast enough. So this is more on the sort of most simplified level of how you can model plasmas, which is the Grad-Shafranov equations. So you solve that and you use a simulation, and this sort of does the job for what we want to do here. Now let's look at the rewards. There's a number of things you might want to do or need to do in increasing complexity. The first one is basically you need to keep the plasma alive. It's an unstable problem. If you don't do anything, it sort of goes up or down. So you have to have a stabilizing control and make your plasma not sort of slam into the wall and die. The second thing you might want to do, well, now it's alive. Now I want to sort of say where it is. And basically, maybe you just do this by controlling the centroid here, say where this is, and maybe the plasma current, which sort of goes into the plane here. But the ultimate thing is basically want to do shape control. So really want to basically control sort of the shape of this configuration, also what these null or X points. And very importantly, also these legs. And these legs are actually important for power production, ultimately, because this is where the heat is being dumped on, and we're going to come back to that. So this is literally what we were doing. So this is where the 40 targets come from, because now you're tossing, like a lot of these things, you have a lot of shape points around it. You're going to see them in the video, and that you want to track. You have maybe a leg, a strike point, maybe other things. And so you're formulating big rewards. We're mashing them together by piping, squashing them through sigmoid functions, making them between 0 and 1, and then softmax. And so that you can now combine, and so the plasma physicist, you can discuss with the plasma physicist and ask them, so what would you like to do? Formulate the reward, and then the reinforcement learning algorithm takes care of finding a controller that does that. This is one of the first things we did. So this is basically sort of a little exercise where the plasma goes through different shapes. In the beginning, it's nice and round, high up. Then it goes into a diverted configuration, and then it goes down and does this like sort of shape where it has legs. And then, so these blue points are the tracked points, right, which sort of show that we can actually do this quite nicely. On the left side, you have a fancy view into the tokamak, how this looks like. And you can actually see, in particular, when it comes down, you see that the null point lighting up. And it's very interesting, actually. The part that you can see is not the plasma. The part that you see is the edges of the plasma where the plasma cools down. The plasma itself is invisible. So that's sort of what you see here. Now, how much time do I have left? About 10 minutes?
So you have
15 minutes. Ah, okay. Oh, easy. Okay, cool. Yeah. Yeah, I'm happy to take questions afterwards, of course. Great. Okay, cool. So the thing that I showed you on basically on the first slide is sort of like our first exercise where we try to see, well, is this actually even possible, right? Is the simulator good enough? Because even though simulations exist, I mean, when you do reinforcement learning, as we said before, right, they sometimes get exploited, or the reinforcement learning algorithm works differently with the simulator than a human. Is it working? And so this was the proof that it's possible. But it's just to say that for shapes like this, we have controls that work. So PID with some observers works very well. Also for this, however, the more complex your field becomes, the more difficult it is to find a control, and you always have to do a new controller. And it's not uncommon that basically it's sort of like a big part of a PhD topic to sort of find a new shape and sort of stabilize it, right? And then maybe study it a little bit. And so the idea is like, and as we said, right, the physicists would like to sort of study them. And the idea is, can we actually now use these methods to sort of speed this up a little bit and do sort of rapid prototyping? And this is what Sophie Gorno at EPFL did with a bunch of people at DeepMind. So sort of use these methods to sort of rapid prototype a shape. And she was interested, or is interested basically in this like lower part here of where the heat gets dumped, right? So this is, as we said, so this is the plasma here, and then the particles would travel sort of around the outer flux level in the end and sort of go down here and hit the wall here. This is what is called the diverter, and this is basically where the heat production would happen. And you have to imagine this point gets a lot of heat in a very small, so this is just like, you know, a few square centimeters. So the idea is, could you possibly have several of the strike points, right? This is called a strike point. And there are some shapes, right? These are only a little bit more complex if you see like the field configuration, right? Where we can sort of distribute that. The question is, can you do more? And here's sort of this jellyfish configuration, which they found, where basically you can actually now distribute sort of the heat over many different strike points. By the way, there's another one here, but this work was about the lower part because you study sort of, there's a length concept that you can study and lots of interesting things. Anyway, this goes into technical details, but so there's this shape, and this is what's found with reinforcement learning, basically by sort of Sophie and people at DeepMind, so Timo and others going together and saying, okay, what do we want to do? Formulate the reward, turn the crank in the learning algorithm, having a policy, then go on the plant and run it. Now, what happened on the plant was a little bit different than what you see here, but it sort of gave the physicists sort of enough room to sort of say, okay, here's something interesting, tweak it, and then design, actually, ultimately they designed their own controller again, then to stabilize this jellyfish configuration. You can then, you know, throw all your diagnostics at it. I'm not going to go, I appreciate that you're not plasma physicists, that it's not so interesting. I mean, Thomson scattering and, you know, heat radiation, God knows what. But maybe the cool one that we can look at is, because we all understand, is like the visible light camera. So the Mantis camera, it's called. I just watched this here. So this is a view into the blood on the, so it's flipped over, but you sort of start seeing the leg here, right? The shape. So this is that part here. It's going to come back, and then you see down the legs, and you have to flip it over mentally, right? It's so. Here it's coming. So this X point here, legs. And sort of the plasma up here. And these are just different sort of viewpoints. And you can sort of see the clock here, right? This goes all very fast, so this is very much slowed down. Anyway, so yes, so you can run this, and then the physicists can study the properties of that and do all the good stuff. Okay, so I'm almost at the end. I just want to sort of close it up by saying a few things. First, maybe a word on models. I said that in the beginning, right? This is maybe controversial to some, or maybe surprising to some, or maybe not. I don't know. Maybe the world has moved on from that. But practitioners of RL actually make a very heavy use of models. And actually, in my experience, I mean, some people just are a little bit oblivious of that fact that they really do that, interestingly. But they do it in different ways, right? Usually it comes through a simulation. So you bake your world model in let's say, Mujoko simulation or like FGE, right? And then you sample from it. But of course, you can use the world as its own model. But even then, right, if you look how people work, so the practice, right, this is why I like to actually open the view a little bit, involves like very heavy use of simulators. Usually have a quite good simulation, use the simulation a lot to design rewards, to design their algorithms, see what works, what doesn't work, before they go onto their precious system and trash it, right? And so basically, and what if you don't have that, right? So the plasma reactor goes a little bit in that direction, because it turns out that this FG simulation is not quite good enough for some things we might want to do. And now what? What do we do, right? This gets really hard. And since not everyone has a plasma reactor in the basement, or you know, can ask the supervisor to buy them one, we thought we built sort of like a little benchtop system where we can do this kind of things, and that actually sort of is very quickly sort of too difficult to actually simulate, or simulate in a way that is useful for reinforcement learning algorithms. And this is sort of like a pneumatic setup where we have 9 valves here, plexiglass, sort of 2D, and we can throw in ping pong balls or other things, and then you can ask, well, can I servo this using, can the agent, right, activate this servo valves and sort of servo this ball around, maybe little shapes, or have several balls and stack them, and very quickly can understand that this is very hard to simulate. And I mean, if someone comes and claims, well, I can simulate a round ball in a steady field, sure, I can make it unsteady immediately. I can throw another shape in there, and I will very quickly be able to generate a situation where you will not be able to simulate this in a very effective way, right, for reinforcement learning. And sort of this forces us a little bit to think differently about it and how we could do reinforcement learning on systems where maybe we don't know anything, can do discovery. Anyway, this is just a shameless plug, obviously, for Mohawk's poster that is going up for the paper today, so go talk to him if you want to know more, or you can also chat with me, of course. Good. All right, I look back. Let's look forward. Are we done? Well, not quite, because interestingly, even though we have a lot of success with reinforcement learning, I think, and maybe I'm just blind, but I mean, and come talk to me and give me examples, and if you know of, I would actually be interested. There's not too many RL deployments in the real world. I mean, by real world, I mean not just an ICRA video or where your robot does something. I don't mean just a real system in the real world. I mean an application where people care that things work 24/7, robustly, stably, God knows all the good stuff, right, and want to make money with it. And this is obviously where classical control engineering shines. I mean, control engineering runs our world, right? And we don't see, the question is a bit, why is that? Well, we still have to formulate the RL, we're not sort of absolved from formulating the control problem. We just have to do it in a different way. We have to find the right way to set up the RL problem. What this means is usually you have to bring people with domain knowledge together in machine learning people, because there's rarely one person or one group that has all the knowledge. And it's really, from own experience, it's really hard. It's really time consuming to do that. You have to have a RL suitable simulator, right? I mean, even though people sometimes have simulations, turns out they're not necessarily what you can use for RL directly, so you have to tweak it together with the domain experts, a lot of work again. So you need domain knowledge, you feed it, but you can only feed it through sampling. That's awkward sometimes. Could we do differently, maybe? And that's obviously maybe bringing me to, you know, the big elephant, the LLM elephant in the room. Maybe the latest crop of machine learning models can help us with that, but how, right? So think about it. You know, and then also want to sort of drive that point home. I think like many traditional control problems are, the system is designed with traditional control in mind. And basically, if you just go to like a random little tracking problem somewhere and you replace it with RL, it's not going to do anything useful most of the time. It's not going to do better, because basically the system is sort of designed and boxed in a way, and the specification is such that this is exactly what we want. RL is not going to shine there. So RL as a simple drop-in replacement is not the right thing to do. So you have to step back and rethink things a little bit more holistically. This often means also design changes, or in the overall sort of workflow or design of your control system and problem. Right. So I was saying that basically there were 3 steps, and due to a lot of progress, we sort of have, to a large extent, solved this part. Sure, there's a lot of work we can still do on interesting technical details, and there's contributions to be made. But I would say the intellectual burden has, and this is not just because of reinforcement again, right? I mean, if you can solve a PID controller LQR, do it, right? And then move on. But you first have to understand that you can do it, and that's where the intellectual burden is. So it has really shifted, or remains really high for 1 and 3. And that's basically where we spend a lot of like sort of sweat and blood, intellectual energy to do. And yeah, the question is, will this change? How will it change? So if we meet again in 10 years, well, hopefully we meet a little bit earlier, can we look back and say, well, the world has moved on again, and we're now solving 1 and 3 sort of in a very automatic way, so that, you know, your first year PhD student can solve the control problem on day 1, write up and go home. No, do other things, more interesting things. All right. that's it. That's all I have. I hope we have a little bit of time for questions.
So thank you, Jonas, for this nice tour. Questions? Yeah, we have one here.
I'll phrase it a bit confrontationally. Why don't we have working fusion reactors yet? Is it because the modeling is insufficient and it works in simulation, but there's some gap to reality? Or is there something in addition to that?
Very good question. It's not because of control, actually. There's also, I would say, there's not one single thing. There's many, many things. It's a tremendous engineering and scientific challenge. There's certain scientific things which we don't know yet. Then there's certain engineering challenges that still have to be solved. But actually, interestingly, if you talk to people in the field, they would actually say, well, it's money, or it used to be money. Because if you look at what has been spent over the last 30, 40 years on fusion research, it was very little in comparison to a lot of other things. And if that would have changed earlier, probably things would have moved on a bit quicker, right? But that's just to say there is still engineering and scientific things, but it's many, many. So there's not one single bottleneck. The way how we think, and this is probably a little bit the thrust of your question, the way how we think about where this becomes useful, very useful, is that now people can think, right? For future generations of reactors, people can think about differently about the control. They say, I have now this reinforcement learning, machine learning, data-driven approaches in mind. What does that mean for me when I design my control system, right? And so we're actually sort of in interaction with this community to see where this is going. And I think that's going to basically have a huge influence. Because one important thing you also have to realize, once you have the first fusion reactor that sort of does energy production, so it's called Q larger than 1, you still have to make it affordable. So you have to iterate quite a bit. And the faster you can do that, the better it is. And I think this is where all this will start to play a big role. I hope that makes sense.
Yeah, Alessandro?
As a follow-up, the sort of mindless question, the big elephant in the room to me is assuming the technological infrastructure for this tokamaks is in place, would you trust deploying your RL-based controller in the real world?
Great question. Yes. For the following reason, you're not going to deploy it just like that, right? There's going to be other stuff. And why could we actually deploy it on TCV? Let's take this example. It's because it's a safe system by design. There's many different reasons why there's safety stops. And so basically, if our reinforcement, and we have triggered safety stops that they haven't triggered for 20 years because we did things differently, right? And oh, there's this safety stop that we actually have in there. Or you can do safe control, right? Safety filters. I think we heard about safety filters on day one. And obviously, so like safety is a systems property. You have to think about this holistically. And I think this algorithm will help us in some parts, right? The performance part. And you have to combine it with other things. And this is software safety, hardware safety, all that. And that's the reason why I'm saying, yes, I would trust it, assuming that people do their job in the rest of the part. Yes.
Yeah, maybe a final one, John.
So I was hoping for an opinion on, there's a lot of, in RL, deep RL and so on, pixels to actions type work, right? With video games, with robots, simulators, now autonomous driving for years. Is that the right place to put deep RL? Because you could also think of it as a lower level thing where you just tune local actions, or you could think of it as a global, more on the strategy, and then rely on other stuff in between. Yep. It seems to me like you have a huge hammer, try to hammer this beginning to end. Is that the right way to go about it?
Yeah. No, it's an excellent question. There's sort of two aspects to that, right? One is sort of the academic question, see, okay, what works, right? If I just think for a second, like, can I solve it with that? And, take my algorithm and try to solve it. Now, the other part is like, is this the right way ultimately to do it in the real world? And if I want to do applications and things like that. I think your question goes a little bit in that direction. And the answer, I think, is no. It's not always the right thing. And this is a little bit what I maybe was alluding to with that last point, is like, you have to think about the problem in a holistic way. So what is the best way to deploy RL? And this is actually not always an easy question, right? If you think about self-driving, where would you deploy RL in that? And the answer cannot be like end to end. I think it's a bad idea. But that doesn't mean that there's not good places where you can use RL in that whole stack that will make things easier overall, right? I mean, overall, somehow you have to pay for software complexity, deployment complexity, maintenance, and so on down the line. So how do I use RL to actually make something useful? And there are places for that because there's big sub-problems, right, which you can sort of box away and still sort of have this flavor of like, okay, there's a complicated system dynamics that it's hard for me to model, so maybe I can use it in a data-driven way. Yeah, I think that's sort of sorry, it's not very a concrete answer because I mean, I obviously cannot go into all that details, but yeah, I think there's places for this. That makes sense. But I think you have the right sort of the right question. It's a good question, right, to ask.
Okay. I think we should stop with questions here. Thank you, Jonas, once again.